Welcome back to the deep dive, everyone. This is the place where we really get into the weeds of complex engineering topics, breaking them down so you get the core ideas you need. Yeah, if you're building systems, managing them, or honestly, even if you're just curious about how large-scale software holds together, well, you're in the right place. We try to give you that shortcut to really understanding this stuff. Okay, let me set the context right away. We are picking up where we left off, continuing our deep exploration into the fundamental building blocks of distributed systems. We're basing this series heavily on the structure and insights from the book, Patterns of Distributed Systems. Now, this is crucial. This is episode 2. If you happen to miss episode 1, where we talked all about chapter 1, where the why of distribution, the limits of single servers, all the ways things can fail, you really should pause and go back to that one first. Seriously. Chapter 1 laid out all the problems. Today, with Chapter 2, we start looking at the architectural answers, the patterns that solve those problems.
That's exactly right. Chapter 2, it's called Overview of the Patterns. Think of it like a guided tour. Our job today is to start mapping out and digging into these common techniques, these patterns that engineers use to deal with all that failure and coordination complexity we discussed last time. And just to be clear, we're not getting bogged down in like specific Java code or Go implementations here. Not yet, anyway.
Right.
What we're learning is the pattern language. It's this shared vocabulary, this high-level shorthand. Experienced folks can say, okay, we use a write-ahead log here, probably need an idempotent receiver on the front end, and boom. Everyone understands the implied design, the trade-offs, the behavior. It's like having a shared set of Lego bricks for building these massive systems.
A distributed Lego set. I like that.
Yeah.
Okay, let's unpack this then. Chapter 2, overview of the patterns, block by block. Where do we start?
We start at the absolute foundation. Before we even think about multiple machines talking, we have to make sure one machine can keep its own house in order. Data integrity.
Right. Making sure the data itself stays consistent, even if the power cord gets pulled, right?
Right.
So yeah, the most basic challenge just on one server. How do you guarantee data is sound if the server crashes right in the middle of doing something? The book uses that widget transfer example.
Exactly. Let's say you have a node, call it Neptune. It's moving 40 widgets from Boston to Pune. That seems simple, but it's 2 steps, right? First, you decrease the count in Boston. Second, you increase the count in Pune.
Okay.
Now, those are probably 2 separate writes, maybe to different files or different places in memory. There's this tiny window of time, but it's real. Where Neptune could crash after writing the Boston change, but before writing the Pune change.
And the widgets just vanish. Poof.
Oof, gone. 40 widgets disappear into the ether. The system's state is now corrupt, inconsistent. That's unacceptable, obviously. So the bedrock solution, the first pattern we really need to understand is pattern 1. Write-ahead log or wall.
Write-ahead log. Okay.
The idea is actually pretty simple, but incredibly powerful. Before the server even tries to make those tricky, possibly multi-step changes to the actual data files or its main memory structures, it first writes a description of the entire intent to change everything needed to perform the operation into a special, separate log file, sequentially.
So it logs the intent first, like writing down, I'm about to move 40 widgets from Boston to Pune before actually moving them.
Precisely. And critically, it writes this log entry atomically, as a single operation, and ensures it's durable, meaning it's actually hit the disk before it proceeds.
Why is writing to this one log file inherently safer or easier than just updating the Boston and Pune records directly?
Well, it comes down to how storage works, especially spinning disks, but also SSDs to some extent. Doing one single sequential write, just appending to the end of this log file, is generally much faster and more reliable for the hardware than doing, say, 2 separate random writes to different locations on the disk, which is what updating the Boston and Pune files might involve. The system forces that log write to complete, to be flushed all the way to the physical storage before it even thinks about touching the main data or telling the client, okay, done.
Okay, that makes sense. So you have this durable record of intent. How does that help when the crash eventually happens?
Right, so Neptune crashes mid-widget transfer. When it restarts, the very first thing it does is consult this write-ahead log. It reads the log entries. If it finds the log entry for the widget transfer, it checks the actual data state. Maybe the crash happened before the Boston Pune update started. The log entry is there, but the data hasn't changed. So the recovery process simply replays the operation described in the log. It performs the decrement and increment. Widget saved.
And if it crashed after Boston was updated but before Pune?
Same idea. The log entry contains enough information, often the before and after values, or just the operation itself, to figure out what state the data should be in. It sees Boston is done, Poon isn't, and it completes the Poon update. Or maybe it rolls back the Boston change if the log indicates that's the safer path to consistency. The point is, the log provides the ground truth to get back to a consistent state. No lost widgets.
Okay, that recovery sounds solid, but performance. If every single little update needs to wait for a synchronous write to disk, doesn't that just kill throughput? I mean, disk writes are slow.
Yes. That is absolutely the trade-off. You're trading some latency for that guarantee of durability and consistency. And you're right, naive implementations can become bottlenecks. There are different types of logging, like physical logging recording the exact bytes changed, versus logical logging recording the operation like add 40 to Poon. Logical logging is often more compact. But the main performance mitigation technique is something called group commit. Instead of flushing every tiny log entry to disk immediately, the system buffers several log entries in memory.
Collects a batch.
Exactly. It collects a batch and then writes that entire batch to the disk in one larger sequential I/O operation. This amortizes the cost of that slow disk flush over many operations. You get much better throughput, though maybe slightly higher latency for individual operations compared to an immediate flush.
Okay, group commit helps. You also mentioned this wall is critical for more than just single node recovery.
Well, absolutely fundamental. Think about replication. If you have multiple servers, say Neptune, Jupiter, and Saturn, if they all start from the exact same initial state, and then they all process the exact same sequence of operations from an identical write-ahead log.
They have to end up in the exact same final state.
Precisely. Determinism.
Yeah.
That identical log stream becomes the basis for keeping replicas in sync. It's how we build towards fault tolerance using multiple machines. The wall isn't just for recovery. It's the foundation for replication.
You also hinted that these log entries don't live forever. They can be discarded eventually. Something about a low watermark.
Right, yeah. The log can't just grow infinitely, otherwise you'd run out of disk space, and restarts would take forever reading the entire history. So logs need to be truncated or compacted. The low watermark, or LWM, is basically a pointer, an index in the log. It marks the oldest log entry that the system absolutely must keep to be able to recover its current state.
How is that point determined?
Typically, it's tied to snapshotting or checkpointing. Periodically, the system takes a complete, consistent snapshot of its entire data state at a specific log index. Think of it like a full backup, but optimized. Once that snapshot is successfully saved to disk, all the individual wall entries before the log index of that snapshot are no longer strictly needed for recovery. The snapshot itself captures their combined effect.
So the low watermark gets updated to that snapshot's index.
Exactly. The LWM advances, and the system can then safely delete or perhaps archive the old log segments before that mark. It keeps the log size manageable and drastically speeds up recovery, because a restarting node only needs to load the latest snapshot and then replay the log entries after the low watermark. #2. Consensus and failure masking and replication. Okay, so the wall gives us resilience on one node, but like we said, the whole point of distributing is usually to handle failures by having copies replication. And that means coordination, getting multiple servers to agree. This is where things get, well, complex, fast.
Right. The scenario you painted, the leader, Neptune, fails. A new leader, say Jupiter, takes over. But how does Jupiter know which updates Neptune had started replicating but maybe hadn't finished? How does it clean up that state safely? It needs a reliable way to order things, right?
Precisely. And critically, it cannot rely on wall clock time. The system clocks will hammer on this point, but they just drift too much. They're unreliable for ordering across machines. So we need logical tools. The first one is pattern 2, generation clock. It's conceptually simple, just an integer counter, but it's maintained by the group of servers. Every time something major happens, especially a leader election, this counter gets incremented. Raft calls it a term. Zookeeper calls it an epoch. Different names, same core idea.
Okay, but the log already has sequence numbers, right? Log index 1, 2, 3. Why do we need another number, this term, or epoch?
Good question. The log index orders events within a single leader's reign, within a single term. The generation clock orders the terms themselves. Imagine the old leader, Neptune, gets disconnected because of a network partition. The rest of the cluster gives up on it, holds an election, increments the generation clock, say to term 3, and elects Jupiter. Now Jupiter starts accepting writes in term 3. Meanwhile, the network heals and suddenly Neptune wakes up. It still thinks it's the leader and it's still in term 2. It tries to send replication messages to the others based on its old log.
But the others are already in term 3.
Exactly. They see Neptune's message tagged with term 2 compared to their current term 3 and immediately reject it. They know it's stale. They might even tell Neptune, hey, you're out of date. There's a new leader in term 3.
So the generation clock prevents that split brain scenario where two nodes think they're the leader and issue conflicting commands.
That's a primary use case. It forces the old leader to recognize it's been deposed and step down. It ensures a linear progression of leadership. Cassandra uses a similar idea, not necessarily for leadership, but to make sure that if a node restarts, any writes it makes after restarting are logically newer than its state before restarting, using generation numbers. It avoids stale data reappearing.
Okay, generation clock for ordering leadership terms. Now, how do we ensure that the decisions made within a term are safely replicated? That sounds like the famous quorum pattern.
Yep. Pattern 3, majority quorum. This is really the heart of consensus protocols like Raft and Paxos. It's all about safety. A quorum is defined as the minimum number of nodes that must agree on something for it to be considered decided by the whole group. And crucially, for safety, this minimum is usually a majority.
Meaning, if you have n nodes, the quorum size is n divided by 2 plus 1. So for 5 nodes, it's 3. For 3 nodes, it's 2.
Right.
Why is majority the magic number? Why not just require 2 nodes to agree, or maybe all of them?
Because of a vital mathematical property, intersection. Any two majority quorums drawn from the same group of nodes must overlap by at least one node.
Okay, let's visualize that. 5 nodes, A, B, C, D, E. A majority is 3. One quorum could be A, B, C. Another could be C, D, E. They both contain C. Another could be A, D, E. That overlaps with A, B, C at A, and with C, D, E at D and E.
Right.
Any two majorities have to share someone.
Exactly. And that intersection is the key to safety. Let's say leader Neptune wants to commit an update, like our widget transfer log entry. It sends the entry to followers Jupiter and Saturn. Neptune needs acknowledgments back from a majority of nodes, including itself. So if Neptune is A and it gets ACKs from B and C, that's A, B, C, a majority of 3 out of 5. Now, Neptune can consider that log entry committed. It's safely stored on a majority.
Okay, it's committed. Then Neptune crashes.
Right. Now, a new leader needs to be elected. To become the new leader, Jupiter, say node D, also needs to get votes from a majority. Maybe it gets votes from C, D, and E. That's C, D, E.
And because both A, B, C, and C, D are majorities, they must intersect. In this case, at node C.
Precisely. So when Jupiter gathers the logs from his voters during the election process, it's guaranteed to see that committed widget transfer entry from node C. It knows that entry was successfully committed by the previous leader because it's present on at least one node in its own majority.
So committed entries can never be lost or rolled back during leader changes because of this quorum intersection property. That's clever.
It is. It's the core safety mechanism.
So the leader knows an entry is committed when it gets ACKs from a quorum. But how does the rest of the system, especially followers or clients, know what's safe to read or act upon?
That brings us to the next piece. Pattern 4. High watermark, sometimes called the commit index.
High watermark? Okay, like a tide line.
Exactly like that. It's an index pointer in the write-ahead log. It indicates the index of the last log entry that the current leader knows has been successfully replicated to a majority quorum of nodes. Everything in the log at or below the high watermark is considered durably committed and safe. Everything above the high watermark is still speculative or in flight. It might have been written to the leader's log, maybe even sent to some followers, but the leader hasn't yet received confirmation from a majority.
And why is this mark so important for clients?
Because it dictates what data is safe to expose. The fundamental rule for client interaction is, a server, whether it's the leader or a follower serving reads, should only return data to a client that reflects log entries up to the high watermark.
So you prevent the client from seeing data that might later get rolled back if the leader fails before that data actually reaches quorum commitment.
Exactly that. It prevents reading dirty or uncommitted state. The leader calculates this HWM. Typically, it looks at the log replication progress reported by all followers, finds the index that a majority of servers, including itself, have acknowledged, and that becomes the new HWM. It then communicates this HWM value to all the followers.
So everyone agrees on the line in the sand for committed data.
Right. The HWM is the practical mechanism that makes the theoretical safety of the quorum visible and usable by the rest of the system, and ultimately by the end user. #tech3, scaling client interactions and responsiveness.
Okay, so we've built this really robust core wall for single node safety, quorums, and high watermarks for distributed consensus and commitment. But this all sounds like it involves coordination, waiting for ACKs, maybe disk writes. It could be slow, right?
Yeah.
If the leader is busy managing all this consensus stuff, how does it also handle potentially thousands of client requests coming in at the same time without getting bogged down? We need patterns for throughput and, just keeping things snappy for the user.
Absolutely. Responsiveness is key. And you're right, the consensus part takes time. Plus, just handling concurrent client requests trying to modify the same state can lead to complex locking, race conditions.
That's a mess.
Not handled carefully. Traditional multi-threaded systems use complex locks, mutexes, semaphores, and they are notoriously difficult to get right. Deadlocks, performance bottlenecks, under contention.
Yeah, debugging those is not fun.
Not fun at all. So a very common and effective pattern, especially for the core state machine logic in these systems, is pattern 5, singular update queue.
Singular, as in one.
1. The idea is to radically simplify the state management by forcing all modifications to happen sequentially. You set up a single queue where all incoming requests that need to change state are placed. And then you have one dedicated thread, just one whose only job is to pull requests off that queue one at a time and apply the state change.
Hang on. A single thread processing updates in a high-performance distributed system? That sounds counterintuitive. Aren't we intentionally creating a bottleneck?
It sounds like it, but it's a calculated trade-off. You're accepting a bottleneck at the point of state mutation, the place where correctness is absolutely paramount. In return, you get guaranteed ordering, elimination of complex concurrency control for that critical state, and much simpler logic.
How does that scale then?
Because only the core state modification is single-threaded. Everything else can still be highly parallel. You can have many threads handling network I/O, accepting client connections, putting requests onto the queue, handling read-only requests that don't modify state, etc. The clients submit their requests asynchronously. They put the request in the queue and maybe get back a future or a callback. They don't block waiting for the single thread to process it. That single thread just focuses on rapidly executing the state logic, which often primarily involves writing to the write-ahead log, something we already know needs careful handling.
Okay, so you isolate the complexity. Where is this used?
Oh, widely. Think about the core Raft state machine applying committed log entries has to be deterministic and sequential. Kafka's log appending is conceptually similar. Many event-driven architectures use this. Modern frameworks with lightweight threads or actors, like Go channels or Akka actors or Java's virtual threads, make implementing this pattern very efficient. You decouple the request acceptance from the execution.
Okay, that handles safe execution order. But what about network weirdness? I send a request, say, transfer $100. The leader does it, commits it via quorum, everything's fine. But the network drops the okay response coming back to me. What do I do as a client? I didn't get an okay, so I assume it failed. I retry.
And you transfer the $100 again.
Yeah.
Big problem. This is the classic issue with non-idempotent operations. An operation's idempotent if performing it multiple times has the same effect as performing it once. Reading data is usually idempotent. Adding $100 is not.
So how do we prevent that accidental duplication?
This is where pattern 6, idempotent receiver, comes in. It requires cooperation between the client and the server. First, the client needs a unique identity, a client ID. When it connects, maybe it registers and gets one. Then, for every command it sends, the client includes not just the command itself, but also a request number or sequence number that is unique for that client. It increases monotonically. So, first request is #1, second is #2, and so on.
Okay, so every request is tagged with client ID request number.
Exactly. Now, the server, before executing the business logic of the request, like transferring the money, it checks a cache or a table. Have I already successfully processed request #N for client ID X? It stores the result of successfully completed requests, keyed by that client ID request number pair.
Ah, so if the retry comes in with the same client ID and the same request number.
The server sees the duplicate combination, says, aha, I've already done this one, looks up the stored result, which is, okay, $100 transferred, and simply sends that stored response back to the client without executing the transfer logic again.
Clever. It makes the non-idempotent operation appear idempotent to the client, even with retries.
Precisely. It guarantees at most once execution semantics from the perspective of the state change, even if the client sends the request multiple times due to network issues. This is absolutely vital for reliable systems. Kafka producers use this exact mechanism to offer exactly once semantics for message publishing. It's crucial for things like creating a unique resource like a lease or financial transactions.
Okay, one more piece for responsiveness. The leader, when it sends out a write request to its followers to achieve quorum, it's waiting for responses from potentially several other machines over the network. It can't just sit there blocking a thread waiting for all those ACKs, right?
Definitely not. Blocking threads while waiting for network I/O is a major performance killer. You'd run out of threads very quickly.
So classic async programming challenge, how's it usually handled?
With pattern 7, request waiting list. Think of it as an internal tracking mechanism. When the leader, acting as the coordinator for this write, sends out the replication request to the followers, it assigns a unique identifier to that whole operation. Let's call it a correlation ID. Then it creates a little context object, maybe a write quorum response callback, that knows I'm waiting for ACKs for correlation ID 123, and I need 2 ACKs to satisfy the quorum. It puts this callback object into a map or a list keyed by the correlation ID.
Like a temporary holding area for pending operations.
Exactly. Sometimes called in-flight requests or somewhat jokingly purgatory in systems like Kafka. The leader sends the requests and immediately moves on to processing other work. It doesn't wait. Now, as the ACK responses start trickling back in from the followers, the network layer looks up the correlation ID from the response, finds the corresponding callback object in the waiting list, and notifies it. The callback logic updates its internal state. Okay, got 1 ACK. When it receives enough ACKs to meet the quorum condition, got the second ACK, quorum met, then it triggers the final action, maybe marking the log entry as committed via the high watermark, and importantly, sending the success response back to the original client.
And it removes itself from the waiting list.
Right. This way, the leader's threads are never blocked waiting for the network. They dispatch the requests, register the callbacks, and stay busy. The responses trigger the completion logic asynchronously. It's essential for high throughput and low latency when dealing with multiple network interactions. Hashtag 5V. Scaling data access, partitioning.
Okay, we've got single node safety with walls. We've got consensus and client handling sorted with quorums, HWMs, idempotent receivers. Now for the really big jump. What happens when one machine just isn't enough? Not enough disk space, not enough CPU to handle the load. Even with all these patterns, we need to spread the data itself across multiple machines.
Exactly. We move from coordinating the log across replicas, which is consensus, to distributing the actual data set, which is partitioning or sharding. This is where we truly scale out the storage and processing capacity.
It feels like a whole different level of complexity.
It introduces new challenges, definitely. Good partitioning aims for a few key things. 1, distribute the data relatively evenly so no single node gets overloaded, avoiding hotspots. 2, make it efficient to figure out which node holds the data for a specific key you're looking for. 3, make it reasonably fast and minimally disruptive to move data around when you add new nodes or remove old ones, rebalancing.
Okay, so how do we approach that? What's the first pattern?
A very common and often simpler approach is pattern 8, fixed partitions.
Fixed partitions, meaning the number of partitions doesn't change.
Well, the number of logical partitions is fixed up front. The key idea is you define many more logical partitions than you currently have physical nodes. For example, you might decide your system will have, say, 224 logical partitions, even if you only start with 3 servers.
224, why so many?
We'll get to that. First, how do you map data to these partitions? You take the data's key, like a user ID or a product's KEU, run it through a consistent hash function, and then use the modulo operator with the total number of logical partitions. So partitioned hash key 124. This tells you which of the 224 logical partitions this piece of data belongs to.
Okay, but where does that logical partition actually live?
That's the second step. There's a separate mapping, usually managed by that consistent core we'll talk about later, that assigns each of those 224 logical partitions to one of your current physical nodes, say your 3 servers.
Got it. Hash determines logical partition, mapping determines physical node. Now, why the large fixed number, like 1024?
Because it makes adding and removing nodes much smoother. The crucial point is, the hash key %124 calculation never changes. A given key always belongs to the same logical partition number. Now let's say you add a 4th server, Uranus. You don't need to rehash all your data. The consistent core just decides, okay, Uranus, you will now be responsible for logical partitions 768 through 1023. It updates the mapping. Then the system only needs to move the data belonging to those specific 256 logical partitions from the original 3 servers onto Uranus.
So you're moving data in predictable, predefined chunks rather than having to recalculate everything.
Exactly. You move only a fraction of the data, roughly nth if you're adding the nth node, and the key to partition assignment itself remains stable. This leads to faster, less disruptive scaling operations. Systems like Apache Kafka and Apache Ignite use this fixed partition approach heavily because it simplifies cluster management and rebalancing.
Okay, that sounds quite elegant for scaling, but what's the downside? Hashing destroys locality, right? If I want to query all users whose names start with S, their keys might be hashed to completely different partitions on different nodes.
That's the primary trade-off. Fixed partitions based on hashing are generally terrible for range queries. You have to spray your query to potentially all nodes and gather the results, which can be very inefficient.
So if range queries are important, what's the alternative?
The alternative is pattern 9, key range partitions. Instead of hashing, you partition the data based on sorted key ranges. Think of it like a dictionary. One partition might hold all keys from A up to, but not including F. The next partition holds keys from F up to L, and so on.
Okay, so keys that are close together alphabetically are likely to be in the same partition on the same server.
Correct. And the huge advantage is obvious. If you need to query for all keys between cat and dog, the system can look at the range boundaries and know immediately, that entire range falls within partition 2, which lives on server Jupiter.
So you only need to query Jupiter. Much more efficient for those kinds of scans.
Way more efficient. This is why systems designed for analytical queries or key value stores that need fast range scans often use this approach. Think HBase, Google's Bigtable, CockroachDB, DB. They all use key range partitioning in some form.
But it can't be perfect either. What are the challenges here?
Two main ones. First, data skew. What if keys aren't uniformly distributed? Maybe you have way more users whose names start with S than X. The partition holding the S range could become massive and overloaded a hotspot while the X partition sits idle. Hashing tends to distribute load more evenly, even for skewed keys.
Right, hotspots are bad. What's the second challenge?
The dynamic nature of the ranges. Unlike the fixed number of partitions, key ranges often need to change over time. You usually don't know the perfect range boundaries up front, so systems typically start with maybe just one partition covering the entire key space. When that partition grows too large, based on size or load, the system splits it into two ranges, really.
So the ranges themselves, and therefore the mapping of keys to partitions, changes dynamically.
Exactly. And conversely, if two adjacent ranges become very small, the system might merge them. This splitting and merging means the metadata, the map of which key range lives on which server is constantly being updated by the consistent core.
That sounds much more complex to manage than the fixed partition mapping.
It is. You trade the operational simplicity and stable mapping of fixed partitions for the query efficiency of range scans. It's a fundamental design choice with significant consequences depending on your workload. #V. Consistency across partitions and time.
Okay, so we've partitioned our data, spreading it across multiple nodes using either fixed or range-based strategies. Now, what if we need to perform an operation that touches data in multiple partitions, potentially on different servers? But we need that operation to be atomic, all or nothing.
The classic distributed transaction problem, like transferring money where the source account is in partition A on server 1 and the destination account is in partition B on server 2. Precisely. How do you ensure that both updates happen, or neither happens, even if server 1 or server 2 or the network fails midway? The textbook answer, though it comes with heavy caveats, is pattern 10, two-phase commit, often abbreviated as 2PC.
2 phases. Sounds ominous. How does it work?
It involves a coordinator node managing the transaction across all the participant nodes, the nodes hosting the partitions involved. Phase 1 is the prepare phase. The coordinator tells all participants, get ready to commit this transaction. Do whatever you need to do, acquire locks on the data, write the changes to your local write-ahead log, and tell me if you can guarantee you'll be able to commit if I ask later.
So each participant essentially makes a promise. They lock resources and durably record their intent using their own wall.
Yes, they have to guarantee that if they say yes, prepared, they will be able to commit later, no matter what, unless told to abort. If they can make that promise, they reply prepared to the coordinator. If anything goes wrong, example, lock conflict, disk error, they reply abort.
Okay, phase 1, gather promises. What's phase 2?
Phase 2 is the commit phase, or abort phase. The coordinator gathers all the replies. If all participants replied prepared, then and only then does the coordinator decide commit. It sends a commit message to all participants. Upon receiving commit, the participants finalize the transaction, apply the changes from their wall, and release their locks.
And if even one participant replied abort or didn't respond in time during phase 1,
then the coordinator decides abort. It sends an abort message to all participants, and they roll back any changes they prepared and release their locks. All or nothing.
Logically, it makes sense. It guarantees atomicity across nodes. But you mentioned caveats. What's the big catch with 2PC?
The big catch is blocking. During phase 1, when a participant prepares, it has to hold locks on the data involved. It holds those locks until it receives the final commit or abort instruction from the coordinator in phase 2.
And what if the coordinator crashes after sending prepare but before sending the final commit abort?
That's the nightmare scenario. All the participants that replied prepared are now stuck. They're holding locks, but they don't know the final outcome of the transaction. They must wait for the coordinator to recover and tell them what to do.
So resources remain locked, potentially for a long time, blocking other transactions. Availability takes a huge hit.
A potentially massive hit. This blocking behavior, especially in the face of coordinator failure, is the primary reason why many modern high-availability distributed systems try very hard to avoid using 2PC for general operations. They might use it for rare administrative tasks, but often prefer other models, like eventual consistency or saga patterns, for more common workflows, accepting that temporary inconsistencies might occur. 2PC prioritizes consistency over availability.
Okay, so 2PC handles atomicity across space partitions. Let's quickly revisit consistency across time. We talked about generation clocks ordering leadership. But we also said system clocks are bad for ordering regular events. Can we re-emphasize why relying on server timestamps is so dangerous?
Absolutely critical to internalize this. Physical clocks on different servers will never be perfectly synchronized. Never. There will always be skew.
Even with NTP, Network Time Protocol.
Even with NTP. NTP helps. It bounds the skew, but it doesn't eliminate it. Clocks drift due to temperature changes, vibrations, even relativistic effects, believe it or not. And the NTP sync itself can be delayed or jumpy due to network latency. Clocks can even go backwards briefly during adjustments. They're not reliably monotonic across a distributed system.
So what's the concrete problem this causes? The book had that example with Alice.
Right. Alice writes update 1, say, decrement Boston inventory, to the leader, Neptune, gets an OK. Then immediately writes update 2, increment London inventory, gets an OK. Then Alice quickly does a read query that hits a follower, Saturn. Now imagine Saturn's clock is running slightly behind Neptune's. It might receive and apply update 2, London first, timestamping it based on its local clock. Then it receives update 1, Boston. Because update 1 logically happened before update 2, but Saturn's clock is advanced, Saturn might incorrectly process or timestamp update 1 as if it happened after update 2 based purely on arrival time relative to its local clock.
So Alice's read from Saturn could potentially see the new London value, update 2, but the old Boston value from before update 1, even though she definitely performed update 1 first.
Exactly. From Alice's perspective, the system is inconsistent. It violated causality. The effect, update 2's result, became visible before the cause, update 1's result, from her viewpoint interacting with Saturn. This happens purely because Saturn relied on its potentially skewed local clock to order or timestamp events relative to Neptune.
Which is why we need things other than system timestamps for ordering.
Precisely why we need mechanisms like the write-ahead log sequence numbers for ordering on one node a leader, generation clocks for ordering leadership terms, and more advanced concepts like logical clocks, Lamport clocks, vector clocks, or hybrid logical clocks, which combine physical time with logical counters, when we need to establish a reliable causal order across different nodes and events without depending on synchronized physical time. #TAG-TAG-SEES. Cluster management and messaging. All right, we've covered data storage, WAL, consensus quorum, HWM, client handling, idempotent receiver queues, partitioning, fixed, range, and transactions, 2PC, plus a time issue. The final layer is really about managing the cluster itself, keeping track of nodes, managing metadata, and ensuring efficient communication between the nodes.
The infrastructure that holds the whole distributed system together.
Exactly. And the core of this is often pattern 11. Consistent core. This isn't usually where your main application data lives. Instead, it's a small, separate cluster, typically just 3 or 5 nodes running a strong consensus protocol like Raft or Paxos. Its sole job is to reliably manage the critical metadata about the main data cluster.
So it's like the cluster's brain or administrative office. It knows who's who and what's where.
Perfect analogy. The consistent core stores and serves information like which nodes are currently considered alive and part of the cluster, which logical partitions are assigned to which physical nodes, who is the current leader for a given partition group, configuration settings, things like that.
And because this metadata is so critical, it needs strong consistency, right?
Absolutely. Operations on the consistent core often require linearizability.
Okay, we've heard that term. Quick refresher. What does linearizability buy us, practically speaking?
Linearizability is the strongest single-copy consistency model. It basically guarantees that from the perspective of any client interacting with the system, all operations appear to take place instantaneously, one after another, in some global order that is consistent with the real-time order of non-overlapping operations.
So it acts like there's only one copy of the data, and operations happen instantly.
Pretty much. If client A writes X, and then client B reads, client B must see X, or some later value, never an older value. There are no stale reads allowed for linearizable operations.
And you need that for critical metadata, like who is the leader?
Definitely. You can't have two different parts of the system getting conflicting answers about who the leader is, or about which node currently owns partition 7. That would lead to chaos. So the consistent core provides these linearizable reads and writes for the metadata, often using consensus protocols internally. It also manages other crucial patterns internally, like lease mechanisms. A lease is like a time-bound lock or privilege. Nodes might need to acquire a lease from the consistent core to prove they are alive. If a node fails to renew its lease before it expires, the core assumes it's dead and can trigger failover procedures.
So the consistent core is the central point of truth. Small, robust, strongly consistent. But you said it's usually small, like 3 or 5 nodes. Why?
Because consensus protocols like Raft get slower as you add more nodes. Getting a majority agreement from 7 nodes takes longer than getting it from 3. So the consistent core itself doesn't scale to managing, say, thousands of nodes directly for high-frequency updates like health checks.
Ah, okay. So if you have a truly massive cluster, thousands of data nodes, how do they efficiently share less critical, more frequently changing information, like basic I'm alive heartbeats or load statistics? You can't hammer the consistent core for that.
Exactly. For that kind of large-scale, less critical information dissemination, we switch to a completely different model, pattern 12, gossip dissemination.
Gossip. Sounds informal.
It is, compared to consensus.
Yep.
Instead of a central authority, nodes share information peer-to-peer. The basic idea is, periodically, say every second, each node randomly picks a small number of other nodes, its gossip partners, maybe 3 or 5, and exchanges its current state information with them. This state usually includes things the node knows about itself, for example, its load, its version of some data, and maybe information it has recently heard from other nodes, often packaged as version values, so nodes know which information is newer.
So information spreads kind of like gossip or a rumor through the cluster.
That's exactly the analogy. It's based on epidemiological models, how diseases spread through a population. The key mathematical insight is that information propagates surprisingly quickly this way. In a cluster of n nodes, a piece of information will typically reach all nodes in time proportional to log n.
Log n. That's very efficient for large n.
Extremely efficient and, very importantly, incredibly robust. If some nodes are down or slow, the gossip just finds other paths. There's no single point of failure like a central coordinator.
But what's the catch? It can't be strongly consistent.
Absolutely not. Gossip provides eventual consistency. Eventually, all nodes will converge on the same information, but at any given moment, different nodes might have slightly stale views of the overall cluster state.
So you wouldn't use gossip for something critical like leader election?
Definitely not. But it's perfect for things where eventual accuracy is good enough and scalar robustness are paramount. Think. Discovering which other nodes are in the cluster, membership. Detecting failed nodes. If you haven't heard from a node via gossip for a while, you might suspect it's down. Distributing load information. Systems like Apache Cassandra and HashiCorp Console rely heavily on gossip for these kinds of tasks in large clusters.
Okay, consistent core for critical, small-scale metadata, gossip for large-scale, eventually consistent state sharing. What about just the basic communication between 2 specific nodes, like a leader and a follower? How do we optimize that channel?
Right, the plumbing. 2 key related patterns here, often used together. First is pattern 13, single socket channel. The idea is simple. When 2 nodes need to communicate frequently, like a Raft leader sending log entries to a follower, they establish one reliable TCP connection between them and reuse that single socket for all communication in that direction.
Instead of opening a new connection for every message.
Exactly. Opening TCP connections is relatively expensive, the 3-way handshake. Reusing the connection avoids that overhead. More importantly, TCP itself guarantees that messages sent over a single socket arrive in the order they were sent. So, using a single socket gives you free, reliable message ordering between that pair of nodes. Systems like Zookeeper and Kafka depend heavily on this.
Okay, so use one persistent connection. But even then, if the leader sends request 1, waits for response 1, then sends request 2, waits for response 2, that network round-trip time adds up, right? The channel sits idle while waiting.
Precisely. That latency becomes the bottleneck. To overcome that, we use the request pipeline pattern on top of the single socket channel. Pipelining means the sender, for example the leader, sends multiple requests over the single socket without waiting for the response to the previous one. It might send request 1, request 2, request 3, all back to back.
Filling the pipe, basically.
Exactly. It keeps the network link busy and allows the receiver to process requests concurrently if possible, or at least process them as soon as it's ready, without waiting for the sender to wait for a response. This dramatically increases throughput and reduces the impact of network latency. It's a form of asynchronous I/O.
But can't you overwhelm the receiver if you just keep sending requests without limit?
Yes, you absolutely can. Uncontrolled pipelining can lead to buffer overflows on the receiver side, increase memory pressure, and potentially even make things slower due to congestion. Head-of-line blocking. So systems that use pipelining must have a mechanism to limit the number of in-flight requests that have been sent but not yet acknowledged. This is often done using windowing protocols or by tracking request numbers, similar to the idempotent receiver, and only allowing a certain maximum number of unacknowledged requests at any time. It's about maximizing utilization without causing overload. Hashtag outro. And that really brings us through the landscape of Chapter 2. It was a conceptual tour, right? We started right down to the single node with the write-ahead log, making sure data is safe locally. That determinism enabled replication. Then we built up to coordinating those replicas using logical time with the generation clock and ensuring safety with majority quorums and the high watermark.
Yeah, and then we looked at making it practical, handling lots of clients efficiently, using the singular update queue, making sure retries are safe with the idempotent receiver, and keeping the leader responsive with the request waiting list.
Then we tackled scale, distributing the data itself using either the stable fixed partitions or the query-friendly but dynamic key range partitions. We touched on the cost and complexity of cross-partition consistency with two-phase commit.
And finally, the governance layer. The strongly consistent core for the really critical metadata using linearizability and leases versus the eventually consistent, super scalable gossip protocol for spreading general state information, plus the network optimizations like single socket channels and pipelining.
Exactly. And the key thing for you, the listener, to take away is how these patterns connect and build on each other. You can't really have a meaningful high water mark without a reliable write-ahead log underneath it. The request waiting list makes sense because you're waiting for a quorum. Fixed partitions rely on a consistent core to manage the mapping. They aren't isolated tricks. They form a coherent architectural toolkit.
Understanding not just what they are, but why they exist, and crucially, what trade-offs you make when you choose one, like sacrificing range queries for easier scaling with fixed partitions, or accepting locking for atomicity with 2PC, or trading instant consistency for massive scale with gossip. That's really the path to designing better distributed systems. Okay, before we sign off, we always like to leave you with something to think about. A final provocative thought based on today's discussion. We talked about fixed partitions versus key range partitions. Fixed gives you that stable key to partition mapping, making rebalancing easier, but it's bad for range queries. Key range is great for range queries, but can suffer from hotspots and requires dynamic splitting and merging. So here's the question for you. If you were designing a brand new distributed system and its primary use case was analytical batch process, think large sequential data scans, maybe like nightly reports, where minimizing data movement during scale out is also pretty important, which of those two partitioning patterns, fixed or key range, would you lean towards prioritizing? And what would you see as the single biggest risk or downside you'd be accepting with that choice? Something to chew on. Thank you so much for joining us for this deep dive into the overview of distributed systems patterns. We'll be back next time to continue digging deeper into specific pattern clusters. See you then.